Okay, yes. Because this is the title of my talk, and then the paper has been written with the cooperation of Maurizio Proietti, who actually was the first co-author. Was involved in this project since the beginning. And then two more, Fabio Fioravanti and Emanuele de Angelis, who developed the implementation of the systems.
Use the microphone, please.
Yes, thank you. So many thanks to Zina, you, Fritz, Sam, members of this committee. I thank also my colleagues and my students. And this talk is going to present some results on program transformation, both in the area of functional programming and logic programming. It's dedicated to Neil Jones, to Valentin Tuchin, and to Bob Page. I remember when he invited me to NYU to give a little short course, 3 or 4 talks on the area, and it was very near to me. I remember a telephone call I received in Rome from New York, and it was Bob realizing that he was going to die in a few weeks or a few days, and he wanted to share with me some thoughts which I still keep in my heart. So programs should be correct and efficient. This was the idea at the time. I'm talking about 1980s, because it was a programming the small, not programming the large. So one program could have been sorting. How do you write a sorting program? You could say, pick up a nice permutation among all the permutations, but this is an exponential program because the number of permutations is exponentially high. So here is where transformation comes into play. You have the specification like a nice, so the sorting program should pick up a permutation which is ordered. And this is the specification. While the program should be maybe bubble sort or heap sort or quick sort. How do you go from the specification to the program? So there are basically 2 techniques. One is the schema transformation. You mean this schema written in for specification becomes this schema for the program. So you once and for all, and so let us see an example. Once and for all, if you have the specification of the function f as given by these 3 equations, you know that by a theorem you have proved once and for all offline that this function f can be computed as the value of the variable t of this imperative program. Notice that from a theoretical point of view, you could say this is not a tail recursive program, because after the recursive call of f, you have to do something more. So actually, it's not granted that you can do without a stack, theoretically. And so there is a whole dictionary of these transformations. You may go from this specification written in a functional language, this is the specification, and you may get the efficient imperative program. Efficient in this case means no stack is needed. But the number of steps, so to speak, you see n is going down by 2, and so the number of steps is basically the one of the... so let us look at another approach. This is transformational approach done by rules plus strategies. It's in many steps. These many steps can be viewed theoretically as the way of proving the schema equivalence. And this was developed by Rod Barstow and John Darlington And Darlington did his thesis on program transformation under Rod supervision, and a few years later, I also a student at Rod. Rod is not in very good health. He's in a house for elderly people. His secretary told me that she would go to visit him for Christmas, but she was not sure whether Rod will remember me, or actually if Rod was able to recognize her as his secretary. So this is the famous function in which this technique, program transformation, was applied in the two-plane strategy. What you do, you basically do some unfolding. You expose the behavior of these three lines in functional program by applying this equation from left to right. So you have that phi of n plus 2 can be computed after knowing phi of n plus 1 and phi of n. And you continue this, and you write, or you depict this finite or unlimited or unbounded binary tree. And you discover some subcomputations. So the left sum of phi of n plus 1 is also the right sum of the phi of n. So you need to compute phi of n minus 1 only once, and then you send this value back up to. So the idea is that by Barstow and Darlington, this step was called the Eureka step, the invention step, like Archimedes said, the Eureka. And so if you join together two functions, the sharing subcomputation will emerge. And we will see now, so the rules, and you have to invent this definition. This is, how do you invent this definition? So what you actually have some rules at your disposal. You have the rule of unfolding and the rule of introducing definition, and then the rule of folding. We will see the effect of this rule. And then the rule of instantiation. If you have an equation, you can just give an instantiation for the variable which occurs in that equation. And then where abstraction, which actually allows you to compute the expression E as the value of a variable once for all common subexpression E occurring on the right-hand side of the definition of F. So what you do, you invent this definition, and then you instantiate it with the value of n equals 0, which by unfolding gives you phi of 1 and phi of 0, and phi of 1 is 1 and phi of 0 is 0. And g of n plus 1, this is the instantiation for n plus 1, so this becomes n plus 2, and n becomes n plus 1. And then you do unfolding, f plus 2 is f, phi of n plus 2 is phi of n plus 1 plus phi of n. And you keep unchanged the second part of the tuple. And then you do this abstraction. You see U occurs twice. This is the common subcomputation. So you abstract away U and V, giving this pair for U, and then you do the magic final step. This pair is actually G of n. So now you have a linear recursion, G of 0 and G of n in terms of G of n plus 1 in terms of G of n. So what was an exponentially growing tree now is a linear going line of recursive calls, and you gain. Work has been done on the power of these mechanisms of introducing functions which do not allow a variant of the algebra. If you only know pluses and comma and tupling, you can prove that you cannot be better than that. You cannot create a faster computation for phi. This is a paper by Zhu. And so then you have to link then the original function to this pair. So you see phi of n is the second component. This is a bit strange because you will say, I have to compute the phi of n. Why you force me to compute the phi of n plus 1 as well? So tupling forces you to compute the 2 while you are. So there is an issue here how to link the definition of phi with the definition of G. So this is much better. You pick up the first component of which is the highest value you compute. And then there is another issue in program transformation. How many times you have to unfold in order to discover all the commons of the computation. So this will be solved in the logic case by strategies. You have a strategy that tells you at least unfold twice, because this is has to do with 2 values. The distance between the body and the head is 2, so at least unfold twice, for example. And you have these strategies. So how to invent strategies? I don't have an answer. We have examples, and we have provided strategies which are going to terminate, and they are going to produce better programs. This is the technology. So too far. I mean, so exponential time, linear time. Can you have lower complexity? Yes, if you change the algebra. If you allow yourself the knowledge of a multiplication and squaring, therefore, then you get down to a logarithmic time. We will go to the Dijkstra challenge. And then if you allow yourself also the exponential, you go to constant time. The phi of n is these 2 values, these 2 roots, etc. It's just this exponential. So in one go, you get the value of phi. Obviously, all this can be, and then if you really want to have the C program or the Java program, you like the imperative programming, then you may apply at the end, once you have a schema flowchart equivalence. So if you have these linear equations, linear recursive equations which are linear, then you get this program which is equivalent. And this is the iterative program for Fibonacci. So no tricks, no difficulties. Every student should understand this because it's just handle, turning the handle, nothing to invent, except the original tupling function. Why I have to invent this definition of G as the tuple of 2 consecutive values of Fibonacci. And so this is the paper written by Dijkstra, who also died. And the date of this is 1976. He wrote a letter to Rod Barstow, and said, I tried this function, so you are very good in the Fibonacci, try this function. In the proceedings, the paper, I did actually this derivation, and so that can be done. The solution by Dijkstra has to do with the matrices, which basically 2 by 2, so there are 4 values, and so, but we know that you can do with 2 values only. So you can even, it's a bit of a saving in space. And if you like, this is the tupling strategy, is the fast, 3 equations, and then applying this schema equivalence, there were people around, a decade before, which just produces a collection of schema equivalences, Walker and Strong. I never managed to know the first name of these 2. One, maybe, I don't remember which, but the other one was also J. Dot. Maybe his first name was J. Dot, or whatever, yes. And so you get down to this computation of the FASC function in applicative language. This is it's a parallel assignment. So these 2 values are assigned to these 2 values. And you get a logarithmic time, and a space is a logarithmic space because of the binary expansion of a number. So what I did in my thesis was to, with Rod, he was very humble. No, Alberto, you cannot put me as a first author, but the ideas were all Rod's ideas. I just turned the handle myself. But basically, lifting up to any linear recurrent relation in any semi-ring structure So you have the two operation plus and times. So also in the Boolean case, this recursive equation can be in any semi-ring abstract algebra, need nothing to do with just plus and times and arithmetics. So, and now we go to non-linear recurrence, which is a Tower of Hanoi game. You know the game, and so you, in order to transfer this disk from peg A to peg B, you transfer recursively n-1 to peg C, and then you do the move because now it's free. You do the move, and then you put back the n-1 disk from peg C to peg B. You do the unfolding. You put together all these calls of Hanoi, and these are the pegs in the proper order. You know, I have the number of pegs and the number of disks and the pegs and the order. You see, I change the order. A, B, C becomes B, A, C, B, and C, B, A. So you have this change of the order of the, and so you have basically a tower of breadth 3 function calls, and but any cut will do because it's like a pebble game. You have to put a pebble in the stop node, starting from 3 pebbles on the bottom, and you can go up, filling the 3 pegs. You see, you have a peg here and a peg here. You can use these two to put a peg here. And so you go, at the end, you will be able to compute F Hanoi of n+1 disks. So in my thesis at that time, how can I discover the existence of a moving cut, racing cut? You can, the existence of a cut going from the bottom to the top. And the cut should be of finite breadth. And this is the Tower of Hanoi, and this is the schema equivalence, you see, and this is the final standard of Hanoi. If you allow yourself only circular Hanoi, so you cannot prove the 3 pegs are not in a line, but they are in a circle, and you allow yourself to move a disk from peg A to peg B, but not from peg B to peg A, not back. So all these versions can be easily treated with the same trick of so if only these circular moves are allowed, the breadth of a cut will be 6. You see, nothing to invent. It's just you do unfolding, and then you discover the existence of a cut of 6 function calls. In this case, it's 3. Okay, then you ask yourself, this is not actually really very important. What is the 15th move when you have 4 disks or whatever? And this can be done in a similar way. But there are, like the binomial coefficient, if you do the unfolding, the breadth is not constant. And so you really need a stack. And so you cannot do better. If this sequence of increasing cuts, going up, it doesn't exist, you have to use a stack to solve this nonlinear general recursion. From a computational theory point of view, of course, because you can reduce all computation to all recursion to linear recursion because you use the Turing machine technique. You do a turn of an handle with a recursive call of the Turing machine. Only the tape changes, but the tape is unbounded. The tape you need for the computation is unbounded in general. So now I'll tell you about this. Tell me when time. Okay, and now, which is the idea, is the inverse of partial evaluation. This may be of some interest for you. So an expression, so when you do folding, you have to see whether an expression up there is an instance of the expression you have now, so that you could fold. So expression can be viewed as a constant and a sub-expression E. In this technique, you view the expression as the result of an application of a function to E. So the context becomes a function. And so you go to a higher order manipulation at this time. Let us see an example of this. So you have this reverse of a list. To reverse a list, you reverse the tail, and then you append at the end the head of the list. And you want to get a tail recursive program for it. So the steps are like this. So you say rev_l is actually rev_l to which you append the empty list. Then you generalize this constant, becomes a variable x, and then you abstract away from this context, from this variable, and you have this function here. And now having this function f, where you also abstract away with respect to L, you get this function f, which is this lambda abstraction. And at this point, rev of L append to A becomes f of L applied to the singleton list A. And magically enough, now f of L has a recursive definition. Sorry, this x should be there. And in this recursive definition, what you gain using also the algebra of the append, that the append function becomes a cons. And so you gain in efficiency. So going to higher order allows you to reduce efficiency, to reduce complexity. So there was this challenge put by Bird, say you have a tree and you want to produce an analogous tree with the leaves ordered, but you are allowed only one visit of the tree. So in a sense you have to suspend. So you see you have two visits of a tree. You collected the leaves, you sort them, and then you replace using the sorted list produced by this sort function, and you put the leaves in the proper order. Try it yourself, you will see that it's a bit complicated, almost impossible. You have to invent another language with suspension, etc. But you can do with lambda. These leaves replace this initial program in which the sorting is done by merge. And this is the final program where this is an application. The function A applied to the argument E2, and these are computed by tupling. And the first component of this tuple is a function. And so, and also requires these four values. Three of them are functions, and one is the list. Nothing to think. It's done by just turning the handle again. Looking at this sub-expression, mismatching, and you promote. Okay, so now we go to the, at least you understood a bit about the functional case. Now, what I show you, only two things. Maybe this one, which is good. So you are given this the logic program, which tells you when a string is in the language A to the n, B to the n. So in this context-free language. And you ask yourself for a program which tells you when a list is not is in the complement of AN, BN language. Basically, you start from this requirement. that this S is a string, and the string is not in the language AN, BN. Notice when you write specification in the functional case, in the functional languages, you will find difficult to express the not specification. Something is not produced by. Why in the logical setting, not comes to you as another logical operator as and or. So we do them, at the end, this is the program you get through unfolding, folding, you see the folding, new 5 requires new 5, new 6 requires new 6. Why new 3 is not there? Because it's just, you don't need it. During the transformation, you see you don't need anymore this definition. And so correspond exactly to the counter machine where you count the A's, where A start from A1 plus 1, when it becomes you subtract 1, and when you get exactly to 0, you get into state which is not a final state. You refuse it. I didn't make all these states. Some are final and some are not final. So this is just part of the picture. But they correspond, all the transitions corresponds to these 3-9 clauses. This is continuation in logic programming. So I will just finish by 2 examples. One, how can you use this technology for proving, for theorem proving, and one for proving properties of any program in any language in which you have the semantics available. So this is a famous Yale-Schutte problem. You say when there is the event of loading your pistol, and then the event of being alive or being dead, and you want to know that after you load your weapon, and then you shoot, and then you are dead, S should be dead, and you want to prove this property of this program, and this can be done by the property is written in first order language, which with the quantifier, with the implication. There is a transformation invented by Lloyd and Topor, which uses negation, but basically this program as a model, if and only if the property gamma holds. After a few steps of unfolding, definition and folding, you get down to this factor. So, and what is the model for this? It's just a model in which there is the only expression. So say a model is a set of atoms. There is only one atom which is G of 0 argument. Is the constant G. You see, G has 0 argument, while Olds has 2 arguments. So final example. How to synthesize? You can do the same for the synthesis of Quine's program. This is the Quine's program. You do unfolding and folding, etc., and you get out of this program, which is the program of solving the Quine's problem. So this is to verify infinite state sequence systems like the ticket protocol, and you have the specification always globally, always in the future. If you put a request, you have to wait, but in the future, you for sure you will going to use that resource. And so starvation, and this is final program. So you have a program for reversing a list, and you put the value 2 at the end. So SNOC is the function which, given a list and a value, puts the value at the end of the list. And so if you start, so let us see the contract for Rev. So if the given list is sorted in ascending order, you reverse. The reverse list is sorted in the decreasing order. So this is the contract for SNOC written as a clause. For assorted written as a clause, and for SNOC, if desorted, and then what you add is the smallest, then the the list you get is still desorted. So you have clauses 13 and clause 14, which express these two contracts. You put all together, and you transform, and this is the transform. And you have now the Aldarica space model constructor, model checker, which will tell that these clauses are satisfied. So there is a model for these clauses. So there is a model, since the transformation rules preserves. Can I go back? No. Anyway, since the transformation preserves the model, then if these final clauses have a model, so also the initial clauses, so the initial contract for reverse and SNOC have a solution. And so they are all. So this is basically everything, but I cannot go on. Why not? Maybe I would like to show. Okay, I can't. What's happening? I don't know. Anyway, there was a picture of the cap, of the father of the cap he received of 1993. But you will have in the proceedings the picture of the cap, which the partial evaluation for making coffee. You put first water, I don't know, you partially evaluate the cap with water, and then you add some grain coffee, and then you get at the end the coffee. I don't know what is, but it's written on the back of the cap. And you will see the picture on the proceedings. I finished. Thank you for your patience.
Alberto, you got it backwards. Remember, mathematics consists of actually taking coffee and turning into theorems, not taking theorems and turning them into coffee. But so we are in the unfortunate situation that we have actually time for questions because we're having a little bit problem getting any online. So is there questions?
So in this process of turning the handle and then looking for a racing cut, right?
Yes,
in the search of a function that doesn't require a tail recursive function that doesn't require a stack, right? Is there a method of deciding whether or not this rising cut exists, or is it just sort of by hand?
I'm not able to answer this question. When Maurizio came in my life, I exposed him to the transformation of logic programs, and so the rest of my life was in transforming logic programs. But then, yes, there is an issue of when you can avoid the use of a stack in a recursion. I cannot point out to the relevant papers, but if you may be in contact, I could be able to give you. But this is work done in the 80s, after Wolfgang and Stork in the 70s. All this. Yes, there are results concerning this. A negative result, this can never be done, and positive results, this can be done, like in termination proofs.
Yes. Okay.
Thank you very much again.